Let's talk about second order linear constant coefficient non-homogeneous DEs some more, where the right hand side is going to be an exponential times some trig functions that also have polynomials attached to them. So let's solve. This will be a very big, long example that should encompass everything that happens in this section. So let's solve our homogeneous. So we have y double prime minus 3y prime plus 2y is equal to 0. Its characteristic equation is r squared minus 3r plus 2 is equal to 0, which gives me r values of 2 and 1. So my homogeneous solution is c1 e to the 2x plus c2 e to the x. So now I got to go and find my particular solution. My guess is going to be some function u, it's going to be a function of x, times e to the negative 2x, just because this is such a big thing. I'm going to guess it's something times e to the negative 2x. It'll make my differentiation easier and my solving easier too as well. So if that's the case, our derivative will be u prime e to the negative 2x minus 2u e to the negative 2x, and the second derivative is the u double prime e to the negative 2x minus 4u prime e to the negative 2x plus 4u e to the negative 2x. If I plug it into dE, that's the second derivative, minus 3 times the first derivative plus 2 times the original. I'll factor out the e to the negative 2x out of everything, and then I will end up with the second derivative is the u double prime minus 4u prime plus 4u, and the minus 3 times the derivative, which is u prime minus 2u, after I factor out the e to the negative 2x again, and then the last part plus 2 times the only thing left after I factor out the e to the negative 2x from y sub p is just u. Combining like terms, I get to e to the negative 2x times the whole quantity u double prime minus 7u prime plus 12u. I want that to be equal to that non-homogeneous part of the dE, which is the 2 times the cosine of 3x, minus the quantity 34 minus 150x times the sine of 3x. Which should have, now I forgot about that, I'm missing something right here. This was all times e to the negative 2x, right? And it's going to go away because both sides have a e to the negative 2x attached to it, so divide both sides by e to the negative 2x, which is never 0, and those go away, so you end up with u double prime minus 7u prime plus 12u is equal to 2 cosine of 3x minus the quantity 34 minus 150x times the sine of 3x. Now the next thing I want to do is take a guess at, well, what should be the form of my u? If the homogeneous of this dE, the u double prime minus 7u prime plus 12u, has either a cosine of 3x or sine of 3x in it, I need to be careful about what I guess. So I just want to check its characteristic equation really quick. Its characteristic equation is r squared minus 7r plus 12 is equal to 0. And you can see that those are real solutions because I get 49 minus 48 under the square root. So I would only have exponentials as part of the homogeneous for this dE. I don't care about the homogeneous for this dE. I just wanted to make sure that my guess was going to be okay because my guess is going to take a while to figure out, so I wanted to make sure it was the right one. So cosine of 3x and sine of 3x are not part of the homogeneous. The way I'm going to figure out the guess, though, is I have a sine of 3x, I have a cosine of 3x, and then the biggest degree polynomial I see on either of them is this one right here. That is a first degree polynomial. So what I need to do is guess a first degree polynomial times sine of 3x plus a first degree polynomial times cosine of 3x. And you got to do that even though this one has a 0th degree polynomial. It's the biggest degree polynomial attached to either one or both of the polynomials. Go with the biggest degree in general. So I'm going to go with my u is going to be a generic first degree, a naught plus a1x times the cosine of 3x plus b naught plus b1x times the sine of 3x. And our author goes with this form, which is why I'm going in that direction. If you'd rather go with like a naught x plus a1, that's perfectly fine. You'll get to the same answer. Your work just might look a little bit different. Okay? So the differentiation, anytime you have a polynomial times these trig functions, gets a bit epic because of how many product rules happen. So take a peek through the work. Make sure I didn't miss anything. But it's just product rule a bunch of times, combining like terms to get down to here. I'm going to plug that into the left side of the dE, and I end up with all of this, which in the end boils down to the thing attached to the cosine of 3x is minus 9a naught plus 6b1 minus 7a1 minus 21b naught plus 12a naught. Plus the things attached to an x cosine of x is a minus 9a1 minus 21b1 plus 12a1. the things attached to the sine of 3x is a 9 minus 9b naught minus 6a1 minus 7b1 plus 21a naught plus 12b naught. And the things attached to the x sine of 3x is a negative 9b1 plus 21a1 plus 12b1. Doing a little cleanup there just to combine some like terms, and in the end I want that to be equal to 2 times the cosine of 3x minus 3 times minus 34 minus 150x times the sine of 3x. Okay, so let's equate like terms. So the things attached to the cosine of 3x are 3a naught minus 7a1 minus 21b naught plus 6b1. That should be equal to 2. That gives us this equation right here. Things attached to the x cosine of 3x. On the left side it's 3a1 minus 21b1, but you'll see I don't have any of those here. There isn't a term like that. So that should give me this equation, 3a1 minus 21b1 is equal to 0. Things attached to sine of 3x. I got a 21a naught minus 6a1 plus 3b naught minus 7b1. And over here, I got a 34, but don't forget that there's that minus out front. So that gives me this equation right here. And then the last one is what's attached to the x sine of 3x. I got a 21a1 plus a 3b1. And over here I have an 150 again. Don't forget that minus out front. So that gives me 21a1 plus 3b1 equals 150. This is a system of 4 equations and 4 unknowns. Solve it however you like. The way I chose to do is I multiplied 3a1 minus 21b1 is equal to 0 by negative 7. That gives me negative 21a1 plus 147b1. You add those two equations together. The other equation being 21a1 plus 3b1 equals 150. That gives me 150. b1 is equal to 150. That gives me b1 is 1. Plug b1 is 1 back into 3 times a1 minus 21. b1 is equal to 0, and I get an a1 is equal to 7. Okay, so now I know b1 is 1, a1 is 7. I plug those into the other two equations. So this one gives me 3a naught minus 7 times 7 minus 21b naught plus 6 times 1 is equal to 2. And this one over here gives me 21a naught minus 6 times 7 plus 3b naught minus 7 times 1 is equal to negative 34. They simplify down to this. I multiply this equation by negative 7, and then I add 21a naught plus 3b naught equals 15 to negative 21a naught plus 147b naught is equal to negative 315. So that leaves me with 150 b naught is negative 300, which gives me b naught is equal to negative 2. Plug a naught into your favorite one of those. Plug b naught back into your favorite one of those ones, and you get a naught is equal to 1. Well, what does that all mean? Because a lot just happened. Remember again, my guess for you was a naught plus a1x all times cosine 3x plus b naught plus b1x times sine of 3x. We plug that into the DE with u's. The DE was just u's. And we got a system of 4 equations and 4 unknowns, which gave us an a naught, an a1, a b naught, and a b1, which you can hopefully all see right there. Yep, got all 4 of them here. 2 of them. There are the other 2. So if you plug those in, you get a 1 plus 7x times cosine of 3x and a negative 2 plus x times sine of 3x. So I found a u that worked. And again, remember, I had started this thought with my particular sum function of u times e to the negative 2x. So now I have the whole thing, 1 plus 7x times cosine of 3x plus a negative 2 plus x times the sine of 3x all times e to the negative 2x. That's my particular, which means my solution overall was the homogeneous c1 e to the 2x plus c2 e to the x plus my particular, which is a 1 plus 7x cosine of 3x plus a negative 2 plus x times the sine of 3x, all that times e to the negative 2x. Okay, so these are long problems if you have an exponential times some polynomials times some trig functions. You will most likely make some mistakes in there. I wrote this ahead of time because I didn't want you to have to check out my scribbles as I went along. So just know that these are indeed long. I mean, this video is almost 10 minutes long now, and I wrote it all ahead of time. So they will take you a while, but here's the thing. Can you imagine having your guess, your particular, looks like this? Trying to differentiate that twice, trying to plug it into the DE, trying to equate coefficients and see what you get. I have tried doing it this way before, and it is about, well, actually I've never accomplished a problem that way. There was always some tiny algebra mistake or differentiation or plugging in or copying mistake that I made that just makes it It's still technically doable, but man, they are rough. So this variation of parameters takes it down to something that you can actually do and take apart in bite-sized pieces. And again, the bite-sized pieces are first saying, well, my guess for this is probably u times some exponential. Doing that thought allows you to remove the exponential, so to speak, so that you're down to a different dE, and the right-hand side is a polynomial times a trig function. Those are bears to do, for lack of a better term. There's no shortcut for those. You just have to guess the generic polynomial times a trig function. If they happen to be part of the homogeneous, then tack on another x until it's not part of the homogeneous. Once you do that, though, then you've figured out what your u is, multiply that times exponential, and then that is your particular.